In this lecture, we're continuing our derivation of the radiation from an arbitrary charge and current source. And so where we left off last time was this result, where we got the electric potential, which contained three terms, a monopole term, a dipole term, and a time-dependent, time-changing magnetic time-changing electric dipole, which we ignored. We said we don't want to consider that case right now. So now in this lecture, what we're going to do is we are going to start considering the vector potential. So in that case, the vector potential A is mu0 over 4 pi, the integral of the current density at some location r prime at a retarded time divided by r and integrated over the volume of the prime system. So we could do all the same approximations to rewrite the r, and essentially what we have is so if we use those same approximations like the Taylor expansion and taking only first order terms in r prime, then r just becomes r. Okay, so I'm not going to go over that again. You can review that in the previous lecture. But what that does is it allows us to take the r out of the integral because r is not in the prime system. So you get mu0 over 4 pi r. The integral now of the current density at a position r prime at a time t0. So again, we can do the expansion on the current density. Anyway, integrating over the volume in the prime system. Now, what you can do is you can look back into chapter 5 and review problem 5.7 in that chapter. And what you would find is that by integrating over this current density at a particular moment in time, what you would get is the derivative of the dipole moment with respect to time evaluated at some particular time t0. Okay, so now we can write down the vector potential as mu0 4 pi r, the time derivative of the electric dipole moment. So we're going to leave it like that. We're not going to invoke the approximation that of the static case just yet. We're going to see where it leads before we apply any approximations. So now what we're going to do is try and find the electric and magnetic fields. And so to do that, we are going to make one approximation. Number 3, which is that any 1 over r squared terms are discarded. So we're going to invoke this idea that we're going to be very far away when we measure the fields than from the source itself. So what we can do now is calculate the gradient of the electric potential. And so we take the gradient of 1 over 4 pi epsilon naught, the monopole term, plus the dipole term. And in this case, we're going to keep the time-dependent dipole term. So that's over RC. Okay, we're going to take the gradient of that. So when we do that, what we get is a 1 over 4 pi epsilon naught q over r squared in the r direction minus 1 over 4 pi epsilon naught, the gradient of the dipole divided by r squared plus r hat over rc dotted into the time derivative of the dipole moment. So I said we're going to ignore any 1 over r squared terms, so we're going to drop that one because of the because of the 1 over r squared dependence. Okay, so then what you can do is you could take a look at the second term. The second term also has a 1 over r squared, but you notice it's it's r hat over r squared. Even so, when we take the derivative of that, that one we can also drop out right here. And so what we're left with then is the gradient of minus 1 over 4 pi epsilon naught, the gradient of r hat over rc times the time derivative of the dipole moment. Okay, so now if we apply that, we have to do the chain rule, and we get minus 1 over 4 pi epsilon naught minus r hat over r squared times c dotted into the time derivative of the dipole moment plus r hat over rc dot the second derivative of the dipole moment times the gradient of the time. Okay, so again, let's drop the 1 over r squared terms. So we're going to neglect that. So what we are left with is minus the gradient of the electric potential is now minus 1 over 4 pi epsilon naught r hat over rc dotted into the second derivative of the dipole moment and this gradient of the time. So now we can take a look at the time. The time that we're measuring is time minus, so the time t0 is the origin time, and time t is now. And so RC is the time it takes the radiation to move from the source to where I'm measuring. And so if we apply the chain rule to that, what we get is minus 1 over c, the gradient of r, which is minus 1 over c r hat. And so what we have is, again, dropping any terms in 1 over r squared, we get that minus the gradient of the electric potential is 1 over 4 pi epsilon naught over c squared r hat over r dotted into the second derivative of the dipole moment with respect to time in the r direction. Okay, so now let's take a look at the vector potential. So the derivative of A with respect to time is taking the time derivative of mu 0 over 4 pi r, the time derivative of the electric dipole moment evaluated at some time t0, okay, so we have to take that derivative. So when we do, that's pretty easy. We just get mu 0 over 4 pi r, the second derivative of the dipole moment with respect to time, evaluated at some time t0. Okay, and so we have those two terms. Before we go on and get the electric field, let's just take the curl of the vector potential. So when we do that, we get mu 0 over 4 pi r, the curl of the time derivative of the electric dipole moment. And now I can write that out as the gradient of our time t0, curl of the second derivative of the electric dipole moment, evaluated at some time t0. Okay, so we're doing kind of a change of variable in terms of the time. And when I do that, I already know that the gradient of the time is r hat. So I get minus mu 0 over 4 pi rc, r hat curled into the second derivative of the dipole moment, evaluated at some time t0. Okay, so now if we put this all together, what do we get? We get an electric field, which is mu 0 over 4 pi r, r curled into r, curled into the second derivative of the electric dipole moment with respect to time. For the magnetic field, I get minus mu 0 over 4 pi rc, r hat curled into the second derivative of the electric dipole moment. Okay, so in the end, this is our answer right here. These two equations now give us the radiation, they give us the electric and magnetic fields for an arbitrary source. So in the end, in order to solve for it, what you'd have to do is you would have to come up with an equation for the electric dipole moment. And once you have that, you can then plug it in and you can solve for the electric and magnetic fields. One thing I should say before ending this lecture is if you look at it, the forms are pretty much the same, and E and B differ by the speed of light, which we're used to seeing, and the electric field is perpendicular to the magnetic field, which is perpendicular to the direction. So again, our radiation that we produce is going to be a doubly transverse electromagnetic wave.